William Nordhaus. He was born in 1941 in Albuquerque in New Mexico. And in 1967, he received his PhD from MIT, Cambridge, Massachusetts, USA. And at that point, he moved to Yale University as an assistant professor, and then you climbed in the ranks, and you've been at Yale University ever since, if I understand correctly, and that's 51 years. Pretty impressive tenure record. And I don't know if you've broken a record, but I hope you will break the record, whatever it is. William Nordhaus has focused on the one part of our resources, has focused on nature, a crucial resource for us, naturally. And the point here is that human activity, economic activity, affects our resources, affects them through climate change in particular. So he built up the area that we refer to as integrated assessment of the interaction between the economy and the climate. So, ladies and gentlemen, please welcome Professor William Nordhaus.
In the interest of modern technology, I will use an iPhone to time myself. Thank you very much. The 2018 award in economic science recognizes the significance of technological change and climate change. These two fields are closely related because both grapple with externalities or spillovers associated with economic growth. They both examine what are known as market failures. In other words, they deal with the inability of unfettered or unregulated markets to ensure that economic growth effectively satisfies human needs while protecting ourselves and our environment. My lecture will focus on part of that, which is climate change, and the challenges nations face in devising policies to slow climate change. Now, while I'm here today and talking today and on the podium today, I'm just one person representing what I think of as an invisible college of people around the world and over time, not just in economics, but in many disciplines. I'll talk about that in a minute, dealing with this broad set of problems having to do not just with climate change, but with the interaction of the economy with the natural world and our interactions with that. I'm here thanks to my parents, to my wife, Barbara, who's been my companion for my entire adult life, my children who are with me, my grandchildren who are with me, my teachers who have been such inspiration, and a substantial number of whom have been on the equivalent of this stage over the years, my colleagues, many of whom are here, my students, some of whom are here, and my critics, I think some of whom are here. And I want a special word of thanks to my critics, because those are the people you learn from the most. And finally, thanks for the institutions. I want to emphasize something that's particularly important to me, and I think actually, although we don't always recognize it, the institutions that have supported us, our schools, our families, which is a mini institution, our schools, our universities, our national academies of Sweden and the United States and other places. And these are the places that mean we live in a magnificent hall like this, or we're in a magnificent hall like this. We live in prosperous democracies rather than in caves and dying at an early age. And without these, I would be a hod carrier in Albuquerque or something the equivalent of that. So my thanks to all of those. Now, coming back to the talk today, we have a climate problem because markets fail and fail badly in the energy sector. They fail because one of the byproducts of the use of energy, in particular fossil fuels, is unpriced and therefore underpriced. Markets put a zero price on this byproduct, this unintended byproduct, this externality, whereas the true social cost of carbon dioxide, as in the particular case, is, as we've learned, high. Just how high, how to put a price on carbon, and how to deal with this is the subject of an extensive body of research, and that's also the subject of this talk today. Economics has developed a toolbox, an analytical toolbox to deal with externalities. As I said, these externalities are the unintended byproducts or spillovers of economic growth. They occur outside the market. They're not captured in market prices. Global warming is the colossus of all environmental externalities. And I have a very terrible picture here of, this is the Colossus of Goya, but I use this because many of you know this, it's in the Prado, but I think of climate change as a menace to our planet, to our future. It's particularly pernicious because it involves so many activities of daily life. It affects the entire planet. It does so for decades and even centuries. And it's challenging most of all because none of us acting alone as ethical individuals can do anything about it to slow the change. And so, like the people huddling there, some of us anyway, are very frightened by the prospect. So let's turn from this art to another art, which is economics, and to the sciences of climate change. And so maybe we'll turn there. So climate change involves many sectors or disciplines, such as atmospheric chemistry, geophysics, glaciology, ecology, economics, political science, game theory, international law, just to mention some of the most significant ones. And because these climate change, it's so interconnected, the parts are so interconnected, we need integrated, what was mentioned earlier is integrated assessment or integrated assessment modeling to deal with this problem in a rigorous way. And there are things, I'll talk about them in a minute, called integrated assessment models that integrate knowledge from multiple disciplines into a single framework or single model. And the models are based on fundamental scientific theories. They're increasingly computerized. They are computerized. We have analysis as well, but the models themselves are generally computerized models of various levels of complexity. My own work on integrated assessment models began in a very simple model of first energy and then later on including climate, and it began in 1974 when I was at the International Institute in Vienna. And then I think of myself as stumbling along for almost 2 decades, trying different approaches. The first one wasn't right, the second one wasn't right, the third one wasn't right. They couldn't capture the things. Partly it was I didn't know the analysis, partly it was some of these areas weren't developed empirically or analytically until in 1992 I finally landed on, like landed on the moon, I landed on what's known as the DICE model, which is just the name of a model. But I think it captures, it's the name of a model, but also captures some of the riskiness that is involved. And I'll talk about a little bit later today the current version of that, which is updated to roughly to today, which has the same basic analytical structure as the earlier model, but has evolved both in terms of parameters, in terms of some of the details of the sectors, but the structure is basically the same as it was in 1992. And the structure of the model is shown in the figure here. I'll just describe it briefly. You have economic growth leading to emissions on the upper left, and that's from our driving, our heating, our cooking, our airplane, our air travel. This leads to rising CO2 concentrations and other forces leading to climate change, and climate change is not just temperature, but it's precipitation, and sea level rise, and many other processes. And then the next arrow, it has impacts, ecological impacts, economic impacts, lower chlorine yields, coastal flooding, ocean acidification, which is actually the other carbon dioxide problem, which I won't talk about very much, but it's bad for crustaceans. And then the next link is climate change policies to reduce emissions, and these would be through different mechanisms such as cap and trade, which you know here in Europe, carbon taxes, which you know in Sweden, regulations, which all countries know, and then that through the policies leads back up to affecting emissions, reducing emissions, and then affecting more, in a greater or lesser degree, climate, economic growth itself. And I put those arrows there and the first two arrows are ones we know about and actually exist. The other two, those don't actually exist in all cases. So this is the circular flow that is part of the modeling that we're talking about today. So I want to say a word. Let's see what we're doing here. I was saying a word about mathematics for just a little bit about mathematics as a language, particularly for people, for young people and students, and who are thinking about what they're going to study. My first teacher and mentor and co-author, Paul Samuelson, was also the first American laureate in economics. And he was responsible for the introduction of mathematics into economics. And his view was mathematics is necessary if we were to understand and analyze complex phenomena. And it's interesting, that point is now part of my brain. It's actually built in just as much as the English language is part of my brain. And it's interesting, the great American physicist, John Willard Gibbs, in a Yale faculty meeting, when there was a debate about foreign languages, he stood up and he said, "Mathematics is language," and he sat down. And he's right. The language, and that language is increasingly part of our lives. It's from the design of the computers that are running the show here, to our power plants, to the medical scans that save our lives. I think mathematics is our future. So, I mean, I think we need to study foreign languages. We need to study all kinds of things, poetry, art, but mathematics is key to so many areas of our future. The language of mathematics is also central to our modeling of climate change economics. I'll just show you a little picture here. I thought I'd show you the mathematics of the model, and here it is. That's all it is. It's a constrained maximization problem. It's kind of simple, so there's a lot of vectors here and times and integrals and so on, and it'll be discretized for the actual computerized model. But any of you who know the modeling and know mathematical economics will say, oh yeah, that's a simple old growth model that we know and love for so many years ago. And those of you who know mathematics will say, well, that's kind of interesting. And those of you who don't, just view it as it's a counterpart of Goya. It's just a picture here. Okay. Maybe not so frightening. I don't know. Maybe more frightening. But don't be frightened. Don't be frightened. So economists have focused on the strategy. So let me just turn now to a little bit of the actual results. So economists have focused on economists and others have focused on strategies to slow climate change, and they're basically three potential strategies. Abatement or reduction of emissions is the one I'll focus on. A second one is removing carbon dioxide from the atmosphere, which would be wonderful, but actually you could grow trees to do that, for example, well, I won't say but. And then there's management of solar radiation through, say, putting dust in the stratosphere. Abatement, the first one I mentioned, is the only realistic and safe option at present. Others may come along, but at present it's all that we have, so I'm going to concentrate there. But I have to say, while realistic, it's also expensive, particularly if we are ambitious. Just to give an example, a common goal of the international, say, negotiations and policies is to limit temperature to 2 degrees C above sort of pre-industrial levels. And estimates are that might cost about 4% of our income over the next century or two. This may be good for nature, but it's not actually all that attractive to voters to reduce their income that sharply. So it shows some of the trade-off. Now, that's abatement. I'll say just a word about damages, because in our economics, what we're going to do is weigh the costs of reducing emissions and slowing climate change or limiting temperature on the one hand with the reduction in damages on the other. So you have to go out and do the modeling. You have to determine what the damages are. And you might say, well, that's impacts easier because like abatement, you need the physics and the chemistry and all that. But actually, damages is just economics and ecology. But actually, damages are much, much more difficult. It's probably the most difficult task in all of our processes that were on that last slide, because it's so far in the future. There are things we don't understand very well. We don't have historical experience of this, so it's actually probably the most difficult. So what I'll do is I'll show you some illustrative results. I suppose these slides will be available, so they will be available? Will they be? I guess they will be available on the website, so some of you who, I know this goes by very fast, but some of you who want to look at them in detail can go back and find them. But I want to show you an example of the results from the DICE model. And this, I want to emphasize, this is only one of many models. There are people in the room who do. I won't point you out, but you know who you are, who are doing other models, and they're wonderful models. There are people around the world who are doing this. The only reason I present, well, the main reason I present it is because I know it, but also it's a simple model, has the virtue of simplicity and comprehensiveness in the sense that it does close all the boxes, the links in that, and other models, some do and some don't. But I would emphasize that these are very simplified models. And so, for example, the climate sector, 2 equations, whereas if you go to some of the large climate models, they'll have 1 million equations. And so these are these don't have the resolution of the most comprehensive and up-to-date models. So let me do, excuse me. So I want to talk about 4 sets of policies, and I'll just mention these briefly. One is what a business as usual, which is basically no policies or minimal policies. A second one is where you balance the costs and the benefits. A third is where you limit temperatures over time to, say, 1.5 degrees, which is the latest objective, or 2 degrees or 2.5 degrees. And a third is my modification of that, where you don't limit it as an absolute cap, but you limit it over an average period. The idea being that actually makes more sense because a lot of processes are a function of averages rather than just the absolute level at a point of time. So those are the 4 that I'll show you some results from. So one is you take these, and just one other thing. So you take this business as usual, what happened, and then let's say if you want to limit the temperature to 2 degrees C, which is in the 3rd bullet there, how can you do that most efficiently? So it's not just any old way, but you've got costs of doing it, and you've got the systems, and you want to find how can I limit it to 2 degrees in the way that's the most, the least costly in the economic sense. So here's a picture that shows. It's a little crowded, but I'll give you a quick rundown. So the top. So on the this is time from 0 to. I've gone to 2150 just to give it a little further depth, and this is then from 0 to 6 degrees C above pre-industrial. We're already at about 0.8 or 0.9. So and then this shows you different paths doing this. And the top path is if we do nothing, and you can see that just keeps climbing, and it's pretty substantial by the 2100 or 2150. And then there are other paths. There's one that have, say, economic cost-benefit path where you balance costs and benefits. And then there's this green one where you limit it to 2 degrees C. And then some of the other ones are where you limit it, say, 2 degrees C with a 200-year averaging, 2 degrees C with a 100-year averaging, or 1.5 degrees with a 100-year averaging. They all look pretty much this. So if you go out and they actually don't look very different for quite a while, and then they begin to diverge after 2050 or so. But they'll have very different paths. But the main thing I want to show you is actually, if you take steps now to implement these, you have quite different futures from very, very high temperatures on the one hand to relatively low for the temperature limiting paths. The next slide I want to show you, it shows you the economics of this. So the green line, the green bars show you, and don't worry too much about the units here on the left. They're present values, but they're just, the bars are what I want to emphasize on. So you can see the damages from doing nothing to the optimal to the temperature limiting. And the damages, obviously, as you limit temperature increase, the damages are going to go down from left to right. And these are increasingly stringent policies from left to right, increasingly ambitious policies. And then, so the damages go down. But then what are the costs? Well, they're not much cost if you don't do anything. But as you become increasingly ambitious, the costs rise. So you want to, what the economics says, well, how are you going to balance these? And if you're, and you can see that the extremes, you have a lot of damages and no cost at one extreme, and a lot of costs and very low damages at the other, and somehow in between you can balance the two. And what you want to think of in economics, or in more generally, is what's the best balance between these two? Is it the optimal? Is it a 2 degree? Is it an averaging period? What different averaging period? So you want to find some balance between the costs and the costs and the damages. Now, economics, just see where I am now. Yep. So economics points to one inconvenient truth about climate change policy, and that is, to be effective, the policies have to raise the price of carbon or CO2. And by doing that, correct the externality of the marketplace. So I think one of the insights of economics that I feel very strongly about is that if you're going to be effective, you have to raise the price, because putting a price on our activities is the only way. I mean, we have to get billions of people in now and in the future, millions of firms, thousands of governments to take steps if we're going to move in the direction we want. And the only way that you're going to do that effectively is to increase the price of carbon. And I would say something about the history of that, because I think it's an interesting scientific story. The idea on carbon pricing flowed from the research on what are known technically as dual variables in linear programming, from the pioneering work of Kantorovich and Koopmans, for which they won the Nobel Prize in 1975. And it's, if you do that optimization I showed you a little earlier, and you just grind through it, and you look at what used to be computer printouts, we don't have those anymore, you would see the dual variables there. And I remember when I looked at it, I just scratched my head. I had no idea what this dual variable on the carbon constraint was. And there were different ones on different reservoirs. And then eventually I realized, and I'll quote from when I first realized, this is what I wrote in 1977, and it's I haven't gone much further than this. Because of the externalities, there are no market or political mechanisms which ensure that the appropriate level of control will be chosen. To implement the efficient path implies that we are implicitly putting a positive price on emissions of carbon into the atmosphere, quote, carbon taxes, as a way of implementing the global policy on a decentralized level. So that was the first time it really occurred to me that to think of this in this way, and so it basically it is evolved over time, and I won't spend much more time on that. I'll just mention that this actually disappeared for a long time and then reemerged about 20 years later in the idea of the social cost of carbon, which is how much it costs to put a ton of carbon in the atmosphere. And that's actually central now to national policies. It's central to the design of climate institutions as setting a carbon price or carbon tax. So over the years, nations have negotiated many international climate treaties, the Framework Convention, the Kyoto Protocol, the Copenhagen Accord, the Paris Accord. How are we doing, you might ask? How are we doing? Is the carbon price where it should be, or is it lower or higher? The answer to that question is that the world carbon price is nowhere near where anyone thinks it ought to be. It's maybe 1/10 of the most modest estimate of the social cost of carbon. The actual global carbon price is essentially zero. And I'm not going to go through the various proofs of that, but I want to talk about why that's a problem and what we might do about it in the file. So as I think about this, the problem here is that these treaties have been ineffective in limiting carbon emissions. I'll show you one graph here, which is the trend in global emissions from 1970 to 2017. Policies have been really ineffective in dealing with climate change, and the reason is because of free riding. And free riding is where you receive the benefit of collective activity, collective action, without paying the cost, without contributing. And in the case of international climate policy, what it means is you get the reduction in damages due to people's efforts, but you don't have to do any costly steps at home. And so I'll just talk, that's the free rider problem in economics, in climate change. So in research on this issue and following brilliant studies of the economics of treaties and game theory, I came to a solution that I called a climate club, and want to talk about that in my last 3 minutes. So what is the idea of a climate club? The idea is that nations can overcome the syndrome of free riding in international agreements if they adopt the model of a club. And a club is an agreement where you know what clubs are. We're all in clubs of various kinds. But there are also international clubs. There's the club of the EU, to which you're a member. There's the club of NATO, which you're not a member, but Sweden is not a member, but is a beneficiary. There's the club of the World Trade Organization, of which we are all beneficiaries. And the idea for a club here is to change the way we think of international agreements, which are essentially voluntary for climate, to make them ones where you not only benefit, but you pay. And for the example that I'll suggest is an international climate club to overcome free riding, is the idea is that you would have club play dues through abatement, but non-members are penalized by having tariffs on their imports into the club region. And so let's say you set a target carbon price of $50 a ton. then nations would have their domestic price through whatever mechanism they would choose at $50 a ton. But if you weren't a participant, then you would have a penalty tariff into the club region. So the dues are abatement, and the penalties are the tariff. And I'll just show you a very simple example. This is from my presidential address to the American Economic Association. And it's a very simple idea here. The bars from left to right are the tariff rates of a club. There are 15 regions in this. And the height of the bar is how many participants there are as a function of each tariff level. And the first tariff level is 0, and that's the basic structure where there's no penalty to non-participation, and there are no participants. But in this simple example for a $50 a ton, as the tariff rates gets up to 2, 3, 4, 5%, you see more and more nations participate. And then if high enough, all nations participate. So we're obviously a long way from the climate club or analogous arrangements, but I think that we should look at this as a kind of model for future going forward. So I think I'll just wrap up here, and I'll just make 4 points to end up where we need to go next. First, we need to accept and understand the gravity of climate change. Scientists must continue their research. And citizens must reject politicians who spread false and tendentious reasoning. That's a very important step. We must establish policies that raise the price of CO2 and other greenhouse gas emissions. We must act locally and nationally, but actions must also be coordinated on a global level. And that's it. And it's clear that finally that we need rapid technological change in the energy sector for the transition. So this concludes my discussion of the economics challenges posed by climate change. And I would emphasize the solution ultimately lies in harnessing human ingenuity to develop and deploy low-carbon technologies. And with that thought, I'd like to turn to the extraordinary insights on the economics of technological change that have been developed by my fellow laureate, Paul Romer. So listen up. Thank you.